AP Calculus. We meet again. Today we're going to be talking about limits, that stuff that you guys did at the very end of remote learning. Section 2.1 of the textbook, we're going to be splitting that up into two parts. It's a little bit different than the remote learning, but I think you guys will catch on quick. So, what are limits? Well, limits are kind of like an investigation of domain issues. For the most part, that's where they kind of came about. As well as an investigation of infinite values. So consider this function right here. We know x equals 2 is a domain issue if we set the bottom equal to 0. But what's really happening at x equals 2? It's not just x can't be 2. There's more to it than just that. All right, so we are curious about x equals 2. F of 2 is not defined. But we're still curious. About what happens when you approach 2. That's a 2, not a question mark. Okay, so the first approach I want to talk about is the numerical approach. So let's say we input this into a graphing calculator, some kind of computer, and we made the units by which it counted x, so like our delta x, our change in x, was very small. And then we just said, all right, check this out. We're getting really close to 2. Really close to 2. Even closer to 2. Closer still. Ah, interesting. A lot of 3s showing up after the 1. That's from the left. So left of 2, it seems like we're approaching a value that just keeps adding a bunch more 3s, which looks like 1.3 repeating. From the right, getting closer, getting closer. Looks like it's 1.3, 3, 3, 3, 3. It's also approaching 1.3 repeating. So it's kind of like from this approach, you can always plug stuff into a calculator and really see what it is. Now, 2, if you plug that in, is an error. But what this numerical approach is kind of saying, it's like, well, yeah, x can't be 2, but if it did, if x could equal 2, y looks like it's really, really, really close to 1.3 repeating, which is 4/3. Yeah. The second approach is just to graph it and see what's going on there. So when we graphed rational functions back in pre-calculus, I kind of showed you guys a couple cases where it wasn't just straight up, you have a vertical asymptote, you have a horizontal asymptote, plot some points here and there. There were situations where if you manipulated both the top and the bottom, or one or the other, sometimes factoring will help deal with the domain issues. So like on top, you can take out an x squared. You're left with x minus 2. On the bottom, you can take out a 3. That's 3 times x minus 2. The factor x minus 2 on top and bottom basically divide each other out, and you're left with a parabola. So it's like this. F of x technically doesn't equal 1/3 x squared. For all, like, it is that. That's what it equals. But what it does is it kind of says, hey, the pattern is that at every single point except one. So to graph 1/3 x squared, you start at 0, 0. If you plug in 1, it's 1/3. All right. If you were to plug in 2, it'd be 2 squared, which is 4. 4 times 1/3 is 1.3 repeating, which is like right here. And then if you plugged in 3, 3 squared is 9. 9 divided by 3, 9 times 1/3, right, is 3. And I'm just using symmetry to get these partner points on the opposite side. And again, if I plugged in 4, that'd be 16/3, which is 5 1/3. And so on and so forth. So the graph looks like this. Except that point doesn't exist. It's an open circle. Sorry, not so close. Okay. But the bottom line is, this right here, it's like every point exists from the left and it's converging to this y value. From the right, it's getting closer and closer and closer to this y value. So the limit as x approaches 2 from both the left and the right appear to be 4/3. Okay? So there's the graphing approach. The third approach is sort of like our computational, algebraic, whatever you want to call it approach. And that I pretty much have done that already. The algebraic approach is to say, if I am trying to compute the limit as x approaches 2 of f of x, by the way, that's the notation for how you do that. You would say, can I use algebra to possibly divide out the domain issue? And we did that on the previous example. It'd look just like that. And you'd say, okay, after I divide out the domain issue, there's no longer a problem with inputting 2 into that function. So I'm going to input 2 into that function. So wherever you see the x squared, wherever you see the x, I'm putting a 2. And computationally, 4/3 is the answer. So yeah, we're going to be playing around mostly with that today. This whole idea that I can use my algebra skills to get it down to a point where you can plug it in. So, our first example. I'm just going to turn this thing off. I don't think I need it anymore. It's going to be the limit as x approaches 2 of 2x squared minus 5x plus 2 all over this. All right. So we'll just call this example 1. All right. You should be looking at these patterns and saying, I see a quadratic on the top, a quadratic on the bottom. If I factor, perhaps the x minus 2, because if you're going to x equals 2 and getting an error, then that means x minus 2 will be a factor. I guess we should check to even see if x equals 2 is a domain issue. 2 squared, 4 times 5, 20. 2 times 7 is 14. 20 minus 14 is 6. 6 minus 6 is 0. All right. Now here, this is interesting. If we know that it creates a domain issue, then we know x minus 2 is a factor of this. So you can just guess and check. We know to get 5x squared, we need 5x. We know to get negative 6, it's got to be negative 2 times positive 3. So there's a shortcut for you. If you felt like, hey, I wasn't following you at all on that, you could go through kind of like the longer way where you say, hey, negative 30, what factors of that add up to negative 7? And it should be, what? Negative 10 and 3? So then you can do the guess and check to say, I know it's got to be 5x squared out front, because it's always first times first to get that. And then I need to create negative 10. So 5 times negative 2 would be negative 10, and then put the 3 there. Not with the x, though. So on top, we can use guess and check factoring. I know it's got to be 2x times x. And they both need to be minuses because the middle's minus and the back and the right part's plus. And, well, shoot, it's got to be negative 4 plus negative 1. Yeah. X minus 2 divided by x minus 2 is 1. So then you're left with the limit as x approaches 2 of a function that does not share the limits domain issue. It's all good now. 2 on the bottom would be 10 plus 3, 13. So it's 2 times 2 minus 1 on top, 5 times 2 plus 3 on the bottom, and that's 4 minus 1, 3, and then 10 plus 3 is 13. All right, so if we were to graph this thing, it would look like this rational function with a tiny hole at x equals 2, comma, y equals 3/13. All right, so we're talking factoring. How about this one? Let's say you're looking at the limit as x approaches 9 of root x minus 3 under x minus 9. We'll call this number 2. All right, so when I plug in 9 into the root, I get 3 minus 3 on the bottom, which is 0. If you recall, though, there's this thing called the conjugate. The idea is, if I multiply by the opposite of root x minus 3, root x plus 3, I can simplify the structure very, very quickly. Because we have a difference of squares on the bottom. And the way that the structure works with that is you square the first, square the last, and there's a minus between them. The top is x minus 9 times this root x plus 3. Now the reason why that's significant is because there's just multiplication now separating these two. This x minus 9 divides out that x minus 9. So we're talking about the limit as x approaches 9 of root x plus 3. There's no domain issue, so just plug in and solve. It ends up being 6. Now this one's a little bit different. Let's say you've got, I'll call this example 3. Let's say f of x is equal to root x minus 2. And we're going to say, let's compute the limit as x approaches 2 from the right of f of x, and that's the notation for right and left behavior. 2 from the left, and then at 2. So the first thing I would do is actually graph it. This is shifted right 2 units, and it looks like a sideways parabola. We talked about that in our last, really the last chapter, right? From the right, it's pretty straightforward that this curve is approaching, well, not approaching, it is. It's exactly 0 from the right. The question is, what do we make of the left behavior? Because there literally is nothing occurring from the left of that. Well, from the left, if f of x doesn't exist, like it literally doesn't have a domain less than 2, then the limit doesn't exist. Remember we put those D and E's? Yeah, this is a situation where that's the case. So if from the right, we're good, but the left is like, I don't think so. The limit at that spot is not even defined. It doesn't exist. So at this point, the limit does not exist. All right. That seems like a good stopping point. I'm going to make another video, though, where we do some examples from the actual homework.